Welcome learners. In today's lecture, we are going to continue our discussion on the damping conditions for a second order, also known as RLC circuits. This is also known as a second order circuit. In our previous discussion, we talked about the natural behavior of an RLC circuit, where we figured out the expressions for the voltage equation that came out to be dependent upon the constants A1 e raised to power S1t plus A2 e raised to power S2t. Now, after that, we talked about three forms or possibilities for the roots in the second order circuits, where we talked about the roots being represented by radiating frequency omega naught square and the Neper frequency alpha square. So this was the first condition. The second condition, if the radiating frequency becomes greater than the Neper frequency square, and the third is what happens if the frequencies are equal to each other. In the previous lecture, we saw the graphical representations of the RLC behavior in terms of their damping responses, and now we are going to continue our discussion with the possibilities or three forms of roots needed for the second order circuits. So for the first case, if this condition appears, we say that this circuit will have both roots being S1 and S2 as shown over here. Both roots will be real and distinct, and this kind of behavior will be known as the overdamp response, and we saw its graphical representation in our previous lecture, that how the voltage or current, whatever we are finding, is going to behave for an overdamp response. Similarly, in the second case, if the radiating frequency omega naught is greater than Neper frequency, which is alpha, then both roots in this case, both roots again being represented by S1 and S2, will be complex and conjugate, and such kind of damping was termed as an underdamped response. And if the roots are equal for the third condition, we say that both roots will be real and equal, and such kind will be known as critically damped response. So this is what we saw in our previous lecture, and based on today's lecture, we are going to continue our discussion on the comparison between these roots, how they are going to behave, and what are going to be the voltages, equations or expressions associated with these three conditions, and what are the roots or the mathematical expressions for roots which were S1 and S2 for all these three possibilities. So let us see what happens for the overdamp condition. So we already have determined the voltage expression for an overdamp response. In our previous lecture, we derived a voltage expression if the system is behaving as an overdamp response. You can visit that lecture. So we got the final voltage expression to be A1 e raised to power S1t plus A2 e raised to power S2t. So this is the expression, or this is the voltage expression that we are going to use if our condition comes out to be an overdamp response. Now, how we can know if the condition is overdamp, underdamp or critically damped? By comparing alpha and omega, where alpha is equal to 1 divided by 2 RC and omega naught can be figured out by 1 by under root LC. And again, these things we have seen in our previous lecture. Now, if you want to find the overdamp response, which steps we need to follow? So the first step we need to follow is to calculate the roots for the overdamp response. when we come to realize from the alpha and omega values that if alpha is greater than omega naught, so we say that this is an overdamped response. And in order to find the steps or solution to a circuit having an overdamped response, we first calculate its roots being S1 and S2, and these roots are calculated by the values given to us in the form of a resistor, inductor and capacitor, where we know that S1 and S2 are calculated by this equation, which is minus alpha square plus minus alpha square minus omega naught square. So S1 and S2 can be calculated from here. In the second step, we need to find the initial condition, where initial condition will be, in case of voltage, what is V0 plus, and we can also find the derivative of this initial condition, which will be dV by dt. And then in the third phase, or in the third point or the step, we need to find the constants A1 and A2, so that once we have A1 and A2 and we have the roots, we can put all these values into the basic equation for the voltage, which is shown over here. So this is the equation for the overdamped response. The unknowns can be figured out by these steps. So A1 and A2 will be figured out by the combination of two equations or variations, where we are going to say that the initial voltage V0 naught is going to be A1 plus A2. How did we reach to this equation? So we stick to our basic equation, which is Vt is equal to A1 e raised to power S1t plus A2 e raised to power S2t. If we put time equals to 0, then we'll be left with A1 plus A2, and thus this is how we reach towards this equation. The second equation, which will help us find A1 and A2 variables, which are the initial conditions, will rely on the rate of change or the differentiation of the voltage. So it can be written as IC0 plus divided by C, and then this is going to be S1A1 plus S2A2. So this is the second equation that is going to help us find the unknown initial conditions of A1 and A2. Again, the second equation comes from the basic equation. If we differentiate this equation and then put time equals to 0, so we are going to get this form of the equation. So this is how we have reached these two equations, which is going to help us finding the initial conditions A1 and A2 for the overdamped response. Now let us have a look at an example to further clarify our understanding of the topic, and let us see how we can find these values. So in the example, we have been given these details. So let us take an example. So we are given an RLC circuit. So this is our capacitor, followed by an inductor, and then we have a resistor. And since all of these are connected in parallel, the easiest approach to find the output will be to find the voltage of it. So the resistor is having a value of 200 ohm, the inductor is having a value of 50 millihenry, and capacitor is having a value of 0.2 microfarads. Since this is a natural response configuration, how do we know this? We know this because there is no applied source to the system. So the initial voltage V0 will appear across the capacitor, and initial current I0 will appear across the inductor. So what we have been given is that for this circuit, the initial voltage V0 plus is 12 volts. This is the voltage which is appearing across the capacitor over here, and the initial inductor current IL0 plus is 30 milliamps, which is appearing across this inductor of 50 millihenry. And we have been asked to find these unknowns, that is the finding the initial current in each branch, which means we need to figure out what is IC flowing through the capacitor, what is IL, and what is IR through the resistor. Then in the second part, we need to find the initial value of the rate of change of voltage, which is dV by dt. Since this is an initial value, so it is going to be a 0 plus. And let us say we finally find the voltage expression, find V of t's expression. So these are the unknowns which we need to discuss given this RLC network. So let us start finding a solution to this problem. So let us say we start with the first unknown or the first part of this circuit and see how we can solve this. So we have been given that the initial currents are provided for the inductor. So since this is a parallel network, we can apply KCL on this. So if we apply the KCL or Kirchhoff's current law, we know that the current flowing through the capacitor plus current flowing through the inductor and current flowing through the resistor should all sum equal to 0. So for the capacitor, we still have no value, but we know that the initial current through the inductor is 30 milliamps. And for the resistor, since we have a voltage appearing across the capacitor, the initial voltage, since it's a parallel network, the same voltage will appear across the inductor and the resistor. So we can say that for the finding the current through the resistive branch, we can apply the Ohm's law of V by R. Thus our equation will be voltage of 12 volts divided by 200 ohm equals to 0. So our equation comes out to be 30 milliamps, and this is 60 milliamps divided by equals to 0, and thus the value of the capacitor, or we'll say IC 0 plus the initial value, comes out to be minus 90 milliamps. So this is the initial value which we got. We can also find the initial value of the capacitor by applying the equation which is C dV by dt, but KCL gives us a quick way or a quick method to solve this problem. Now once we have figured out the initial values of current, let us move to the second part. In the second part, we need to find the initial voltage, which is dV 0 plus by dt, and we know from our steps that dV plus dV by dt can also be written as IC 0 plus by C. Where this equation is coming from, this is basically the equation of the current through the capacitor. So we have just shifted algebraically I and C to the right hand side, and we get this equation. So we have already figured out the initial current through the capacitor, which is minus 90 milliamps, and the capacitance value in this case is 0.2 microfarad, so which is 10 raised to power minus 6 farad. So it comes out to be minus 450 kilovolts per second. So this is the initial rate of change of voltage in this circuit. Now in the final part, we need to find the expression for the voltage V of t. So in order to find the expression for the third part, we need to find the expression for V of t. We are doing an example of the overdamped response, but in any case we can verify it is overdamped or not by just finding the value of alpha, which is going to be 1 divided by 2 RC, and we can find the value of omega naught, and in this case you can have a try yourself. This is going to have that the omega naught square will be less than alpha square, and thus this is acting as an overdamped response. So since this is an overdamped response, the voltage expression in this case comes out to be V of t is equal to A1 e raised to power S1t plus A2 e raised to power S2t. Now we need to figure the unknowns in this equation. So in order to figure the unknowns, let us first find the roots. So S1 and S2 are basically dependent upon minus alpha plus minus alpha square minus omega naught square. So if we are finding S1, then our equation will be minus alpha plus under root alpha square minus omega square. If we are finding S2, then our equation will be replaced by a negative sign over here. So I'll write the answers of S1 and S2, which comes out to be, for S1 it is 5000 radians per second, and for S2 it is minus 20,000 radians per second. So these are the two roots which we have figured from this equation, and we can see that both of these roots are real and distinct, as we just saw in our basic definition in the start of this lecture. So for the overdamped case, the roots should be real and distinct, and we can see and verify that the roots of S1 and S2 are real and distinct. Now we need to find the next element in this equation for the voltage. So we have figured out S1 and S2. Now we need to find the A1 and A2 constants, which are basically dependent upon the initial condition. So in order to find S1 and S2, or A1 or A2, we know that our equation will be V0 plus equals to A1 plus A2. So we know that the initial voltage across the capacitor is 12 volts. So let us input the value. So 12 volt equals to A1 plus A2, or we can say that A1 is equal to 12 minus A2. So this is our equation number 1. The other portion of the equation which we saw in the previous steps, so shown over here, is that these two equations together are used to find the unknowns A1 and 2. So the next portion of the equation will utilize IC0 plus by C, which was basically dV0 plus by dt. We know that it is going to be equal to S1 A1 plus S2 A2. So we have already figured out IC0 plus by C, which is minus 40 kilovolts. So we can just input the values. Minus 40 kilovolts per second is equal to, we already have the value of S1, which is minus 5,000, and A1 plus 20 is, S2 is minus 20,000, A2, and now we have this second equation. So what we can do is we can just input equation 1 into equation 2. Once we find the unknown variable, we can again put back that answer into A1, and finally the response we are going to get. So I leave this simultaneous equation solutions for yourself to find. So the value of A1 comes out to be minus 14 volts and A2 comes out to be 26 volts. Hence our final voltage equation is going to be minus 14 e raised to power minus 5000 t plus 26 e raised to power minus 20,000 t volts for t greater than equal to 0. So this is the output equation or the voltage expression for the overdamped response, and we can confirm that this is the correct voltage if we just put time equals to 0 plus. We can immediately see that we'll be left with minus 14 plus 26, which is equal to 12 volts, and this was the initial voltage which we got in the start of this problem, which is over here. So this means that our solution is correct by utilizing all the mathematical expressions that we have. So now let us move to the second condition of the damping behavior, and that is in the underdamped response. And here we want to know what are the roots for this kind of a condition and what is going to be the voltage expression. So let us now talk about the second case, which is the underdamped response. So for the underdamped response, we know that our condition should hold, which means that the radiating frequency square should be greater than the Napier frequency square. If this phenomena occurs, then what are going to be the roots? So we know that our roots from the previous expression was that S1 equals to minus alpha plus under root minus omega square minus alpha square. So we can simplify this by bringing this negative sign outside the parenthesis or the bracket. So this is an iota term, it will be replaced by j, and I'll be left with omega naught square minus omega square alpha square, because we know that j is under root minus 1. So this is the iota or the complex term. In engineering we call this as value of j. So this is how we are getting it. So finally I can write this as minus alpha plus j, and this term inside the or under the square root can be written as omega d. So this is my first root for the underdamped response, and where we have taken omega d, which is the damping factor, having the value of omega naught square minus alpha square, which is the Napier frequency. Since we know that for the underdamped response the roots are going to be complex and conjugate, so we know that the second root for this response S2 is going to be minus alpha a conjugate minus j omega d. So these are the equations of the roots, or this is how we are going to find the roots once we have the underdamped response figured by the ratio of the resonating and the Napier frequency. Now that we know the roots, let us find the specific equation for the voltage. Let's find the voltage expression for V of t. So we know that initially V of t is equal to a1 e raised to power s1t plus a2 e raised to power s2t. So now input the values of s1 and s2 into this equation. So we can say that V of t is equal to a1 e raised to power minus alpha plus j omega dt plus a2 e raised to power minus alpha minus j omega d multiplied by t. So let us simplify this further in terms of the exponential power. So a1 e raised to power minus alpha t multiplied by j omega d into t plus a2 e raised to power minus alpha t e raised to power minus j omega d into t. So now we have two terms in terms of exponential. So this exponential can be further simplified using a trigonometric identity. So these two terms can be simplified using the Euler's equation or Euler's identity, which is basically we can have e exponential j theta is equal to trigonometric identity of cos of theta plus minus j sine of theta. So let's incorporate Euler's identity into this equation, and thus our equation will now have this form, which will be a1 e raised to power minus alpha t, and this term comes out to be, since it's a positive sign, so cos of theta will be omega dt plus j a1 sine of omega dt plus for the second element a2 e raised to power minus alpha t cos of omega dt minus j a2 sine of omega dt. Further simplification can be performed by taking the exponential alpha t to be a common factor. So we'll be left with a1 cos of omega dt plus j a1 sine of omega dt plus a2 cos of omega dt minus j a2 sine of omega dt. We can further simplify this equation by bringing the positive or real or imaginary parts or separating them. So I can write e raised to power minus alpha. Now I'm going to sum the real parts together for a1 and a2, which is cos of omega dt, plus the imaginary part j a1 minus a2 sine of omega dt. And now in order to differentiate our equation of voltage for the underdamped compared to the overdamped, we can write this term in bracket for the coefficients as b1, and this one can be written as b2. So we can write this equation as such that our equation comes out to be e raised to power minus alpha t, and in bracket I can write it b1 cos of omega dt plus b2 sine of omega dt, and thus this is the voltage expression which we have for the underdamped response, and we can organize it with starting with the coefficient just to have similarity with the overdamped response. So final equation can also be written as b1 e raised to power minus alpha t cos of omega dt plus b2 e raised to power minus alpha t sine of omega dt, and thus this is our final expression for finding the Nash's RLC or an RLC or second order circuits underdamped response. And let us look at this equation and see what the variables are conveying in the information that we are getting from this expression. So in this expression, B1 and B2 are basically the same as we saw with A1 and A2, and which is the initial condition. So the system's initial condition is shown by B1 and B2, which are normally real values. The other element in this equation is the exponential minus alpha t, which is basically a decaying function or a decaying exponential. Then we have cos of omega t and sine of omega t, which are basically the trigonometric identities. They basically give the oscillations of the signal. So these oscillations are happening in terms of the sine and omega t. And now this omega t inside is basically the damping factor. Damping means that the attenuation it will cause to our sinusoid signal. So this is what is happening inside this complete equation, and we can visually see this behavior as well. If we have an exponential, its behavior, a decaying exponential, is something like this. So e raised to power minus alpha t. And if we take a combination of any set, for example, if we take a sine signal with a constant amplitude, so this is our sinusoid. If we add, or basically in this case multiply these equations together, we can have the behavior of an underdamped response, and which we have previously seen in our last lecture. So basically we are going to have a wave or a sinusoid that will keep on decaying and such. So this is basically an underdamped response of the RLC circuit, where the exponential is this envelope which is made over here. So this is the contribution of e raised to power minus alpha t, and omega d is causing the drop or attenuation of the signal. So this is how we get the underdamped response graphically, and this equation basically gives us the voltage expression for the underdamped behavior. Now let us look at finding the constants b1 and b2. It will remain the same as we saw with the previous overdamped condition. So for finding b1 and b2, we utilize the same equation. So if we want to find, so if we have the equation of the voltage as Vt is equal to b1 e raised to power minus alpha t cos of omega dt plus b2 e raised to power minus alpha t sine of omega dt. So if this is our final expression for the voltage, b1 and b2 can be figured out as, if we take time is equal to 0 in this equation, then the only thing left will be b1. So this is how we can find b1. And if we differentiate the same equation and then take time equals to 0, we will be left with minus alpha b1 plus omega d b2, and thus we can find the second variable, or which is the initial condition b2, using the second expression. So this is the way to find the b1 and b2 in this voltage expression equation, and alpha remains the same as 1 divided by 2 RC for a natural RLC circuit. So this concludes our discussion on the underdamped response, and now let us see the behavior of the critical damped response, and then we follow it with an example to further understand this underdamped behavior. So finally, the third possibility of damping is the critical damped. So for the critically damped response, our condition of frequencies is that omega naught square should be equal to alpha square. If this is the condition which we see, then the second order circuit will behave as a critically damped response, which means that the circuit or the signal behavior will be on the verge of oscillation. So for this case, again our roots will be a simple value of minus alpha, which will be minus 1 divided by 2 RC. Again, this value comes from the basic root equation of the overdamped response, and the voltage expression in this case again is V of t equals to A1 e raised to power minus alpha t plus A2 e raised to power minus alpha t. So we can sum up the A1s and A2s together, because e raised to power alpha can be taken as a common factor. So I can write A naught e raised to power minus alpha t. Since this A naught is representing A1 and A2, it cannot be a single variable, because we need to find voltages and currents, and it is not dependent upon a single variable A naught. So what we normally do is we represent the voltage expression by changing A naught into two different variables known as D1 multiplied by t e raised to power minus alpha t plus D2 e raised to power minus alpha t. So this is how we redefine this equation, and thus this is the voltage expression that we are going to use when we are going to find the critical damped behavior. Again, the initial values for D1 and D2 will remain the same as we saw previously, that in this equation put V equals to 0 plus. Thus when we put time equals to 0, we get the value of D2, and to find D1 we just need to differentiate this signal and then apply time equals to 0. Thus our other initial condition D1 comes out to be D1 minus alpha D2. Thus these are the two equations that are going to help us in finding the initial conditions of D1 and D2 in this voltage expression for a critically damped RLC, parallel RLC network. So this is a small description of the critically damped, and the important things being that the roots are now found from these two equations, and the voltage is found from here, and the initial conditions are given from here. So this is how we find the critical damped condition of a natural parallel RLC circuit. Now let us come to another example to further understand the underdamped response. So let us say this is another example, example 2, to understand the underdamped response of the circuit. So again we take the parallel RLC network. This is a capacitor followed by an inductor, and then we have a resistor. At the output we are interested to find the voltage expression. This time around the value of the capacitor is 0.125 microfarad, the inductor is 8 Henry, and the resistor is 20,000 ohms. And we know that the initial voltage is V naught and the initial current going is I naught. So we have been given that the initial voltage in this case V0 plus is 0 volts, and the initial condition is minus 12.25 milliamps. We need to calculate the roots for this equation. Obviously, in order to calculate this, we need to know what is the condition of the circuit, whether it is overdamped, underdamped, or critically damped. Then we can find the rate of change of voltages, which is 0 plus, and obviously V0 plus could be figured out. And finally we need to write the voltage expression for this given circuit. So let us try solving this following the same guidelines which we saw previously. So whenever we start to follow or solve an RLC circuit, we first need to know which kind of condition or damping condition it is. So in order to find this, we always start by finding the Neper and the resonant frequency, where alpha is 1 divided by 2 RC. It comes out to be 1 divided by 2 20k 0.125 microfarad, and the value comes out to be 200 radians per second. Similarly, the resonating frequency omega naught is 1 divided by under root LC, and it comes out to be 10 raised to power 3 radians per second. So when we look at, or when we compare these two equations, we can see that omega naught is a value which is higher than the alpha square, and thus we can confirm that this circuit is behaving as an underdamped circuit, or the response of this circuit is an underdamped behavior. Once we know this, we can figure out that how to find the roots for this equation and the associated voltage. So in order to find the roots and the voltage, we know that this is an underdamped response. So the roots, so the basic voltage equation will be, for this case, Vt is equal to B1 e raised to power minus alpha t cos of omega dt plus B2 e raised to power minus alpha t sine of omega dt. So this is the voltage expression that we are going to utilize to find the voltage for this underdamped response. And surprisingly, this equation doesn't involve the roots S1 and S2, but since the question has asked us, we can find S1 and S2 using the equation provided. So for the part A, S1 is equal to minus alpha plus j omega d, and the second root, which is a complex and conjugate, is going to be this. Now in this condition, we need to know what is omega t. The damping frequency we already know is the difference of the resonating frequency minus alpha square. So once we figured out, because we already have the resonating frequency and the Napier frequency, so the roots can be solved from this equation. So the roots are, S1 comes out to be minus 200 plus j 979.8 radians per second, the unit, and S2 is minus 200. We know it's a conjugate, so it is going to be minus j 979.8 radians per seconds. So these are the roots of this circuit. Although the main voltage equation doesn't depend upon the roots, it does depend upon the Napier frequency. So now once we have figured this out, obviously omega naught was needed, so I'll just write it over here. It is 979.8 radians per second. Okay, so now let us start finding the unknowns in this equation for voltage. Obviously we start by finding the initial conditions B1 and B2. We already know what is alpha, and we already know what is omega d, which is the damping frequency. So in order to find the initial condition B1 and B2, we basically go to our basic equation, and we know that B1 and B2 are basically found using these set of equations for the underdamped response. So for B1 and B2, we can say, so to find B1 and B2, what we can do is, we know that V0 plus is going to be B1, and luckily for us, the initial voltage given is 0 volts. This means that the first initial condition is 0, so we get B1 to be 0 volts. So we have figured out what is B1. Now in order to find B2, we need to apply the differentiation of the equation, basic equation, then put the initial condition to be 0, which also equals to the initial condition of the capacitor as 0 divided by C, and this comes out to be the value of minus alpha B1 plus omega d B2. So now we can find B2 from this equation, but if you look at this equation, we don't know what is IC0 plus. So in order to find IC0 plus, we can directly apply KCL on this equation, and we can see what is the flow of current through IC, IL and IR. So since the initial condition is 0, this means that the same voltage of 0 volts is going to be applied, or is going to be available across the inductor IL, and the same is going to be appear across IR, which means that resistor current is going to be automatically 0. So when we apply KCL to find IC plus, we know applying KCL is going to be the sum of capacitor current, inductor current and resistor current equals to 0. So IC is going to be minus IL, because the voltage is 0, so resistor will have no current. And we already know that the initial current IL is also provided to us, which is minus 12.5. Thus our IC is basically 12.25 millifarads. So this is milliamps, it's a current. So this is the 12.25 milliamps current flowing through the capacitor. Once we know this, we can incorporate this back into our circuit to find B2. So this means we will have 12.25 divided by the capacitance provided is 0.125 microfarad. So it is 0.125 microfarad. It is equal to minus B1 into alpha plus omega d B2. We already have B1, so this portion comes out to be 98,000 equals to minus B1 is almost 0, so we are left with omega d by B2. Thus B2 comes out to be 100 volts because the value of omega d is already 979.8 radians per second. So this is B2, which means our final equation for the voltage will have this form, that Vt equals to 100 e raised to power minus 200 t sine of 979.8 t volts for t greater than or equal to 0. So this is the voltage expression for the underdamped response of a parallel RLC network, and hence we have concluded this problem. So now we have understood the various voltage and root equations for the critically damped structure. Then we saw for the underdamped structure, and then we saw it for the overdamped structure of a parallel RLC network. Now let us move towards the second topic associated with the RLC networks, and that is the step response of RLC circuit. So we are done with the parallel response, and now we want to know the step response of this kind of a circuit. So for the step response, it's a very straightforward solution because the circuit associated with this will be, so again we are going to have our circuit elements connected in parallel, capacitor connected to an inductor, and then it is connected to a resistor, and again we are interested in finding the output voltage because in parallel we have this liberty. Initial voltage appearing is V0 and the initial current flowing is I0. So for the step response, what we normally do is, for the same circuit we apply a certain time or a switch, and then we apply a current source to it. So this is now a step response. So the configuration is now a step response where the circuit will open at time equals to 0. When time equals to 0, the current source will directly be applied to all the circuit elements, which are capacitor, inductor, or storage element, and the resistor, and then the current will flow as IC, IL, and IR when the source is applied. So when this kind of configuration is given to us, we immediately say that this is the step response of a parallel RLC network. And in order to write the equation for this, it is straightforward that our equation for this kind of step response will be, so we know from the natural response that our equations are V of t, or let me put it this way. So if we think of this circuit as this portion being the parallel RLC network or the natural behavior when the source is not applied, when this case appears, our equations for the three damping conditions are that V of t comes out to be A1 e raised to power S1t plus A2 e raised to power S2t. For the underdamped, the voltage was B1 e raised to power minus alpha t cos of omega dt plus B2 e raised to power minus alpha t sine of omega dt, and for the critically damped, V of t was D1t e raised to power minus alpha t plus D2 e raised to power minus alpha t. So these are the equations which we saw for the natural response of a parallel RLC circuit. Now when we connect a current source and make this configuration as a step response, the equations will remain the same. The equations will remain the same. The only thing that we are going to associate it with this equation is that we are just going to associate the current or the voltage source with this circuit. So this will be the step response, which means that our equation For, let's say, if you are talking about the step response and the equation is for the current, then this is going to be the IF, which is the source current, plus the equations as per natural RLC parallel circuit. Similarly, if we are finding the voltage for the step response, then V of t is going to be the final value of the voltage, V of f, which is the source, plus the equations as per natural response, which means for voltage it is going to be this equations, and you just add the term of the voltage source, which we are calling as the final value. So this is how we write the equations for the step response. And we can see graphically as well that initially we had the natural response as shown over here, and for the step response we are just adding the source, which will basically act as our final value I of f, or it can be a final value of V of f. And this is how you write the equations for the step response. Let us have a look at an example on this. So let us say we have this example to understand the step response. So we again say that we have an RLC circuit. So this is our capacitor connected to an inductor, and then it is connected to a resistor, and the output is again at the far end. And we say that for the resistor our value is 400 ohm, our inductor is 25 millihenry, and our capacitor is 25 nanofarads. And to make this configuration as a step, or we have been given this configuration, so we are going to have a switch, and then we are going to have a source. In this case we have a current source, so it is I of s, and the switch is going to open at t equals to 0. So the source is having a value of 24 milliamps, and we have been given that the initial energy stored is 0. So this is what has been provided to us, that the initial energy stored is equal to 0, which means that the IL and V naught equals to 0. And we know that at time equals to 0, a DC source of 24 milliamps is applied to the circuit. As soon as 24 milliamps is applied, the circuit works as a step response. What we have been asked is to find the initial currents in the circuit, which means we need to find what is I of C, I of L, and I of R. And then we have been asked to find the rate of change of current, because this is a current source, and then we need to find the roots of the characteristics equation, or roots of the equation. Again we have to see which kind of behavior it is, and finally the expression for this current I of t for time greater than equal to 0. So these are the unknowns that we need to find for this problem. So let us see how can we solve this. So we can immediately look at the circuit and see that there is a current source, which means that this circuit is going to be a step response. But what is happening when time is less than 0? So when time is less than 0, we have been provided that initially energy is 0 in the system, which means when energy is equal to 0, the initial currents in the system is also going to be equal to 0. Since there is no energy stored, this means that IL equal to IC equals to IR, everything is going to be 0. Similarly, the voltage appearing across the capacitor is going to be 0 volts, because the initial energy is 0. So we can say that for part A, everything equals to 0. What about the second part? The second part is the rate of change of current. So in order to find the rate of change of current, we know that voltage is equal to L di by dt. Since the voltage is 0, everything is equal to be 0. There is going to be nothing, because switch because at time is equal to 0, there was no energy. Now let us come to the third part. So in the third part, we need to find the root of the equation. Before we find the root, we need to verify what kind of condition is this. So we need to find alpha, which is 1 divided by 2 RC, and we need to find omega, which is 1 divided by under root LC. So the value of alpha comes out to be 5 into 10 raised to power 4 radians per second, and the value of omega comes out to be 16 into 10 raised to power 8 radians per second. So this is what we are getting. So this is for the omega square. Similarly, alpha square, if we go to it, so it will be 25 into 10 raised to power 8 radians per second, and we can directly see from here that the value of alpha is greater than omega, which means that omega naught square is less than alpha square. So this is an overdamped response. So since this is an overdamped response, we now need to find the voltages and the roots accordingly. So for the overdamped response, our roots are S1 equals to S2, or we can say that this is S1 and S2 is minus alpha plus minus alpha square minus omega naught square. So if you incorporate this value, S1 comes out to be minus 20,000 radians per second, and S2 comes out to be minus 80,000 radians per second. So these are the roots for this equation, and hence we have solved the third part of this problem. Finally, we need to write the expression in the last part of the IL or inductor current when time is greater than or equal to 0. When time becomes equal to 0, the switch gets open, which means that all the current will now start flowing through the storage elements, capacitor, inductor, and the resistor. So when this happens, so for part D, we need to find the equation for voltage. Since this is an overdamped response, what we can do is we need to find the current. So IL of t will be IF, which is the source supplied, plus the equation for the overdamped response was A1 e raised to power S1t plus A2 e raised to power S2t. In order to differentiate it from the voltage and say that this is current, we just introduce the bar sign on A1 and A2. Now we know that this is the equation that we need to find, and again what I wanted to explain for the step response was that the equations remains the same. We just add the source value, considering this to be an I of f value. So this is the equation that we need to fill, but we need to find A1 and A2. So A1 and A2 is now found through the same way that we consider IL at time 0. So in this equation we'll put time is equal to 0, so we'll get the value of A1 bar plus A2 bar, and if I differentiate this time dIL by dt and then put equals to 0, I will get S1 A1 bar plus S2 A2 bar. So this is the rate of change of current. So using these two equations and substitution method, I can find A1 and A2, and thus A1 bar equals to minus 32 milliamps and A2 bar equals to 8 milliamps. So once I have this, I incorporate it over to my final current expression. So IL of t will be, IF is the current source, which is 24 milliamps, and the remaining expression will be such. So my equation or final equation comes out to be 24 plus minus 32 e raised to power minus 20 kt plus 8 exponential minus 80 kt amps for t is greater than or equal to 0, and thus this is the expression for the unknown current for this step response of an RLC circuit.